as I mentioned before, you are very welcome back to this session with our keynote speaker, and I'm personally delighted to introduce Jocelyn. I've known Jocelyn for many years. She was born in Lurgan in Northern Ireland, and just resonating some of the things from earlier today, she went to a school where the policy was that girls don't do physics and science. In the late 1960s, she accidentally discovered pulsars, which was a lovely accident. Okay, and this led to a very vast career involving lots of astronomy all over the world, but in particular, she now is a visiting academic in Oxford and the Chancellor of the University of Dundee, Scotland. She has been the president of the UK's Royal Astronomical Society, and in 2008, she became the first female president of the Institute of Physics, which covers the UK and Ireland. And I'm personally involved with IOP, and I remember Jocelyn as the president, and she did fantastic work at that time, and her good work is still with us in terms of IOP policies. In 2014, she was the first female president of the Royal Society of Edinburgh, and she was one of the founding members of the Athena SWAN scheme. She has received many awards and many honors, including the Breakout Prize, which was in the order of $3 million in 2018. And Jocelyn set up a fund to be run by the Institute of Physics, which donated the entirety of the fund to promote underrepresented ethnic minority and refugee students into the world of physics research. So there's no doubt that Jocelyn is a major hitter in the world of STEM, and she has a very, very busy time, and we're delighted that she's taken the time to join us here today. She's going to talk to us about the discovery of those pulsars, and the title is Discovery of Pulsars in Context. Jocelyn is going to join us later on for the discussion panel. If you have any comments or questions, please do post them into the chat. I will keep an eye on those and relay them to Jocelyn at the end of her presentation. So Jocelyn, it's over to you, and in advance, thank you.
Thank you very much, Paul. Am I heard okay? And can my screen be seen? Great. Thank you very much for this invitation. I'm very sorry I can't be present in person. I would love to have been, but we are doing things as we can in the current situation, and one day we'll get back to some sort of normal. It may be a new normal, but never mind. So what I'm going to do is talk a little bit about radio astronomy, about quasars, which were some of the first radio astronomy sources detected in the sky, about being in Cambridge, UK, the discovery of pulsars. I'll talk about some near misses if I have time. I'll talk about what are pulsars if I have time. But I'm going to keep pretty strictly to time because I know you've got another session shortly after the end of this one. So just to remind you, this is the electromagnetic spectrum, stretches all the way from radio waves, which are on the left of this diagram, through the visible, which is the tiny rainbow in the middle, and up to X-rays and gamma rays on the right-hand edge. Long wavelength is at the left-hand end, short wavelength at the right-hand end. And these days, we actually do astronomy right across this spectrum at all these wavelengths, as well as doing astronomy using some particles, and as well as the relatively newly discovered gravitational radiation, which is a whole other spectrum as well. So astronomy has a lot of ways of observing the universe these days. So I'm going to focus mainly on radio astronomy, which is down the left-hand end of this spectrum. So radio astronomy started worldwide at the end of the Second World War. It happened particularly in the countries that were victorious, because they managed to acquire some equipment from the countries who were not victorious. And in particular, Britain acquired a certain amount of radar kit from Germany by way of reparations. Some academics who had been doing war work returned to their universities at the end of the war, and a number of those who were physicists took with them some of the radar equipment, especially the radar receiving equipment. They weren't terribly interested in the transmitting stuff, but the radar receiving equipment they put to use as radio astronomy detectors, radio astronomy telescopes, asking the question, are there things up there in the sky that emit radio waves? Now, they already knew that the sun gave radio waves because it had jammed some of the radars during the war. There is a story, a scurrilous story, which might not be true, which says that the Japanese knew that there was something that jammed their radars. It was low in the east in the morning. It was high in the southern sky in the middle of the day, and it was low in the west in the evening, and they could not work out what it was. I'm not sure I totally believe that, particularly the bit about they could not work out what it was. It was, of course, the sun. So by the end of World War II, they knew all too well that the sun could give out radio waves. The question was, are there other things in the sky that will emit radio waves? And note, I don't say, are there other things in the night sky? Radio astronomy can be done day and night because the sun doesn't dominate the daytime sky in radio. The sun does give out some radio waves, but it doesn't outshine everything else. It doesn't prevent you seeing anything else in the radio waves, the way the visible sun does stop you seeing the stars. So radio astronomy is quite civilized. You can do it day and night. And curiously, most people work days most of the time. This particular image is of the big radio telescope at Jodrell Bank and a lovely setting sun. The radio telescope was built in the 1950s. It's recently been given World Heritage status, which I think is wonderful. Although it's a major headache for the University of Manchester, who own it, because they've got to keep it standing. So post-World War II, a number of radar experts returning to academia turned their radio dishes, their radar receiving dishes, towards the sky and found they could pick up a number of quite strong objects. They weren't sure what these were. They turned to their optical astronomer colleagues and said, what is there at such and such a position in the sky? And gave its coordinates. And the optical astronomers would say, well, there's something that looks a bit like a star, although it's not a star of any kind that we have known before. So these things became known as quasi-stellar, or quasi-stellar radio sources, or quasars for short. So far, so good. But then there was a very interesting development. In the Netherlands, a Dutch man, not in the Netherlands, working in California, Maarten Schmidt, had got an optical spectrum of one of these funny star-like things that gave strong radio waves. And he couldn't make sense of the spectrum. He couldn't see what chemical elements were producing the lines that he saw in the spectrum. And then he suddenly had an off-the-wall thought. My God, that looks like hydrogen, but it's in the red end of the spectrum. It's got a redshift. Now, redshift means the object is moving away from us, receding. And a large redshift means it's receding fast. By this stage, they knew the universe was expanding, and the deeper out into space you looked, the faster the speed of recession that you found, the faster the speed of expansion. So Maarten, suspecting he's got something with a large speed of recession, suspects he's got something that's at a considerable distance. The snag is, as you know, by and large, distant things are fainter. And yet these things were flipping bright. So what's going on? He went along the corridor to where a colleague, Jesse Greenstein, was puzzling over the spectrum of another of these quasars, the optical spectrum. Jesse was in the process of writing a paper trying to show that this object was made of tellurium. I think it was tellurium. It was something unusual like tellurium, because tellurium was the only spectrum that he could even get approximately to fit what he observed. And Maarten comes into the office and says, Jesse, could it be hydrogen with a large redshift? And Jesse tries it, and he finds, yes, it can be. And it's also a large redshift like Maarten's, although it's a different redshift, which in a sense is reassuring. So these two have been forced to conclude that these bright radio emitting objects are at one hell of a distance. Maarten reputedly went home from the office to his home that evening and said to his wife, something terrible happened at the office today, because he was really quite alarmed by the consequences, the consequences for physics and astronomy of what he and Jesse appeared to have concluded. They were actually right, they were correct, and it's now well established that quasars are both bright and very, very distant. We now know that they contain a massive black hole in their centers, and that's what's responsible indirectly for this massively strong, bright signal. So fast forward a few more years till I'm finishing my undergraduate degree in physics in Glasgow, and I'm going to head south to Cambridge to do a PhD. Now, you probably understand the nuances of British geography, but let me just spell them out. As Paul has said, I started life in Northern Ireland. Number one. I had some of my secondary education in the north of England at the boarding school at 2. I went and did my bachelor's degree in Glasgow at 3. I had decided before I left school that I wanted to be a radio astronomer. I would do a bog standard physics degree to begin with as a good broad training, and then I'd aim to do a PhD in radio astronomy. I tried to get into Jodrell Bank. I didn't. I didn't think I'd get into Cambridge. I thought I was probably heading to Sydney in Australia to do my PhD there. But the academic year in the Southern Hemisphere starts later than here in the Northern Hemisphere. I had a few months in hand, and I thought, well, I'll put in an application to Cambridge anyway, just in case. Not really expecting to get in. And much to my surprise, I did get in. I've spent quite a lot of my life in the south of England, not all of it, but quite a lot. And I think there is a perception by those in the south of England that they are the ultimate civilization, and the further north and west you go, the more uncouth become the savages. Until then, I had spent all my time in the uncouth savage area, so I did feel a bit of an outsider in Cambridge. I also felt an outsider because I was one of very few women. There were only 3 colleges out of about 3 dozen that were for women, so we were a small minority. And most of that minority were undergraduates, and I was a postgraduate student. And I really felt that a mistake had been made somewhere along the line. The place seemed full of young men, Southern English young men, totally convinced of their own brilliance and totally convinced of their right to be in Cambridge. And I thought, yeah, they've made a mistake admitting me. They're going to discover their mistake. They're going to throw me out. This is classic imposter syndrome. We didn't name it. Indeed, we hadn't even identified it or labeled it back then. But now those of us who work, particularly in prestigious places, are on the lookout for imposter syndrome. Students who come up in September, October for the first time are overawed by what they find themselves in, decide that a mistake has been made, and take themselves off home within the first week, if we're not very careful. So we now recognize imposter syndrome, but it was not identified then. So I was pretty certain they'd made a mistake admitting me, they were going to throw me out. But I wasn't going to take myself off home until they threw me out. And until they threw me out, I decided I would work my very hardest so that when they threw me out, because I knew they would sooner or later, when they threw me out, I wouldn't have a guilty conscience. I'd know I'd done my best and just wasn't bright enough for this really esteemed place, Cambridge. It was also a little bit uncomfortable during the first week in Cambridge when the new graduate students in radio astronomy got each presented with a set of tools. This is my set of tools. I still have them. They were actually the first tools I owned. These are not microelectronics tools. These are full-size wire working tools. Actually, there was always one or two curious guys called theoreticians. They didn't get given a set of tools, but the rest of us did. And I was going to spend a lot of the next 2 years wire working and quite heavy physical work because I was involved in building a radio telescope. So this photograph taken in early 1967 is towards the end of those 2 years. The technician, Don Rolfe, on the left and myself huddled up on the right are testing the impedance, testing the connectivity of connectors that I have just put on some air-spaced cable, very expensive low-loss cable, which you cannot coil up and take indoors. I spent the first 2 years working out at the Radio Astronomy Observatory, helping build an enormous radio telescope. My responsibility was all the cables and all the connectors. And there were quite a few miles of cable. The telescope is large. I'll show you a photograph of it in a moment. It's the equivalent of about 57 tennis courts. It was relatively cheap, partly because they used student labor to build it. And about 6 of us worked for 2 years on building it. And as I say, my job was all the cables and connectors. This is the finished article. You can think of this as like 2048 of those old style TV aerials, you know, the ones that look like a capital H. Well, imagine about 2,000 of those all joined up. The wooden posts are the most obvious things. They're actually simply there to keep all the wires away from the wet grass, because wet grass is an electrical short. You can see there's a lot of copper. It's gone that lovely blue-green color. There's almost 200 kilometers of wire and cable in that antenna. At that stage, the university, well, the radio astronomy group was still using valves, vacuum tubes. I'd used transistors in my undergraduate project in Glasgow. And when I said to them, why don't we use transistors? Whoa, noisy, whoa, unreliable. They did ultimately change, but they stuck with vacuum tubes, valves, for a surprisingly long time. So 6 of us spent a couple of years building this, and then after 2 years when it was done, the rest of the 6 melted away, and I was left to operate this radio telescope. What was it for? Well, it was to find more quasars, because they're the hot, sexy topic at the moment, with big questions about what's going on. We only knew of about 20, we needed a bigger sample. And this was a technique devised by my supervisor, Tony, from an idea generated by another female radio astronomy student. So if we look at the top part of this diagram on the right, up top there is a quasar. It's very distant. It's way off the top of your screen, like up about the ceiling of your room. The sun is off to the left, and coming off the sun is a stream of plasma, which we call the solar wind. This plasma is not smooth. It's got clouds that have slightly enhanced electron density and gaps where there's less electron density. When a radio wave from the distant quasar comes down, it has to come through this medium to reach us on Earth. And sometimes from a quasar, the radio wave comes through a cloud. If I use my pointer, through a cloud. Sometimes the clouds have blown past and it's coming through a gap. When it comes through a gap, we see it at full blast. When it comes through a cloud, we see it a bit dimmer. And as the clouds go past, the strength of the signal from the quasar bounces up and down, as there's cloud, no cloud, cloud, no cloud, cloud, no cloud, and so on. And this is about a time scale of 1 second. If alternatively we have the other kind of radio object that was known at that time, a radio galaxy, it's quite broad, and we see it at the same time through some gaps and through some clouds. And so the clouds going by doesn't produce the same changes in brightness. It doesn't scintillate. This phenomenon is called interplanetary scintillation, because it's the interplanetary medium, the stuff between the sun and the planets, that causes this scintillation or twinkling. This analogy is not completely correct, as physicists will know, but it'll give you some idea. Imagine it's a sunny day, you're lying on the bottom of a swimming pool looking up, and there's this pattern of light and dark that blows past you as the wind blows across the surface of the swimming pool. And you see both bright and dark and bright and dark and bright and dark and lots in between. It's that kind of fluctuation that we were picking up in the radio. So my job was to operate this radio telescope, survey the sky, and look for radio sources that twinkled or scintillated. To do that, you have to have a short integration time. If you average over 5 seconds, 10 seconds, you lose a lot of the signal. You see here, this is 1 second time scale. You really need to observe with an integration time of a fraction of a second. So we were observing with 1/10 of a second integration time. I was the first person to operate that telescope, and having debugged it and got it operating nicely, which was relatively easy, I was lucky. I then observed for the first 6 months, and I found about 180 more quasars. So I got the number up from 20 to 200-ish, and we had a good sample. But there was something else that came along as well with the quasars. At that time, the University of Cambridge had one computer. It occupied a room. It was made like, you know, your spare bedroom, that size of room. It was large because it was made with these valves or vacuum tubes. It wasn't with transistors. And very few people could use it because it had memory like your laptop. And I had no access to that computer or any other computer. My data came out on rolls of paper chart. And this image shows me analyzing some of the chart. There was 30 meters of this stuff came out every day. I Did a complete sky scan every 4 days. So one sky scan is 120 meters. That alone is a horrendous amount of paper. And by the end of 6 months observing, I had over 5 kilometers of the stuff. I got quickly used to identifying the scintillating quasars, the twinkling quasars, which is what my job was. I also very quickly got used to identifying man-made human interference. At that time, cars were badly suppressed. And if a car drove down the local road, my radio telescope could pick it up. Sparking thermostats gave radio signals, arc welders gave radio signals. At one point, the Home Office allocated the local police force our frequency. So we had a merry week where we picked up the police force only and no sky until we got them moved. There are bands that are meant to be kept empty of transmissions so as we can do radio astronomy. So I also got used to identifying interference. And just occasionally, in amongst all the quasars and the interference, there was one signal that I couldn't properly classify. Now, it often was not there. 80% of the time it was not there. And the first few times I saw it, I marked it with a question mark and moved on. This picture actually shows the very first sighting of it. And towards the right-hand side, you can see some low-level radio interference. That really is low level, let me tell you. Normally the interference would be, end stop to end stop of the pens, just completely covering the whole chart. But this is some low level interference. And this is the funny signal that I couldn't properly classify. And I think the first few times I saw it, I marked it with a question mark. But the human brain, at least those of us who are trained as scientists, the human brain is good at solving puzzles. And this particular signal was a puzzle. And after I'd seen it a few times, my brain said, in amongst all these miles of paper, "You've seen something like this before, haven't you? You've seen something like this before from this bit of the sky, haven't you?" And then it's easy, because I'm scanning the sky in what we call declination strips, like latitude on the sky. And I store all the rows of paper for each declination strip in a different shoebox. So I find the shoebox that covers this declination and get out all the old charts and lay them out lined up so that the prime sources always came at the same point. And so I've got what we call right ascension lined up. And yep, you can see interference, and it doesn't occur at the same sidereal time. It can occur all over the place. But just occasionally at this particular time, 19 hours, 20 minutes, or 19 hours, 19 minutes, in about one occasion out of 4 or 5, there'd be something a bit like this. Now, regularly it was not there, but when it was there, it was coming from the same coordinates in the sky. And the human brain is really remarkable at retrieving information. This bit of information occupied about 10 parts in a million of all the chart paper that I'm scanning. I showed it to my supervisor, who rightly observed that, look, it occupies 1/4 of an inch, 5 millimeters. We can't see what's going on. We need an enlargement. And with this old chart paper technology, enlargement is easy. You run the paper faster under the pen and everything gets spread out. But you can't leave it permanently running like that, because it gets through a roll of paper every 20 minutes. And guess who has to live at the observatory putting a fresh roll of paper in every 20 minutes, day and night? Next best solution, the graduate student, it's always the graduate student, goes out to the observatory at this time, switches to high speed, lets it run for a few minutes to about here, and switches back to the standard speed. And I did that for a month, and I made high-speed recordings of receiver noise. The thing, whatever it was, had disappeared. And my thesis advisor was furious. You know, it's a flare star, it's been and gone and done it, and you've missed it, Jocelyn. It's always the grad student's fault, isn't it? And then one day I got it. And this is, the labeling came later, let me tell you. Along the bottom are 1 second time pips. They used to be broadcast from rugby and were very, very useful for us. And up here is the signal that came in. And along here, you can see a string of equally spaced pulses. There's one missing in here. Here's a few more. And there's some missing here, but here's a few more. Now let's just look at these. So it's going blip, 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 bump, 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 blip, blip, blip. These come back on beat. Even though it's gone quiet, it's kept the beat. They're in phase. And there's actually hints of some along here that are also in phase. So it's periodic with a period of about 1¼ seconds. This was added afterwards. LGM stands for Little Green Men. So that's what we nicknamed it. Well, I nicknamed it. I regret, but that's what I nicknamed it. But you don't call the first one LGM1. It's not until you've got more than one that you go back and you label the first one number 1. So you can tell that this was added later. So it's local radio interference. It's Joe Bloggs driving down the road from work in a badly suppressed car. No, it's not. It keeps to the sidereal day, the 23-hour, 56-minute day. If it's Joe Bloggs, he's getting off work 4 minutes earlier each day, 28 minutes a week. And this has been going on for a month or two. It's not Joe Bloggs driving home from work. It's faulty equipment. Jocelyn's wired the radio telescope up wrong. We got a colleague who had a separate radio telescope and a separate receiver, but working at the same frequency, to very quietly look and see if they could see it. And they could. They picked it up. That was fantastic. So it's not a mistake that Jocelyn has made. It's something beyond the radio telescope. The snag is both these radio telescopes are on the same site and will be subject to the same local interference. It was also a bit of a puzzle because it's got quite short pulses, which suggests it's very small. A steep pulse, a steep edge to a pulse says it's small. But we already knew after just a few weeks observing that it kept very accurate time. So it's big, it's got big reserves of energy. So it's big and it's small. Yippee. Then a colleague managed to get what we call a dispersion measurement. You'll have seen a rainbow. A rainbow is when a raindrop splits, or lots of raindrops split light up into its constituent frequencies, because the different frequencies travel through a raindrop in different ways. Different radio frequencies travel through space in slightly different ways. In particular, if they go past any free floating electrons, then the high frequencies will travel a little bit faster than the low frequencies. So a colleague took 2 of my receivers, tuned one of them up in frequency, one of them down in frequency, and after some very frustrating time, found that the pulse appeared first in the high frequency receiver, followed half a second later, a quarter of a second later, in the lower frequency receiver. And he knew the difference in frequency between the 2 receivers. This effect is caused by free floating electrons in space. If he makes a guess at the free floating electron density, he can get an estimate of how far the radio wave has traveled, and it comes out to be about 200 light years away. So it's in our galaxy, but it's away beyond the solar system. I kept on observing this because my supervisor wondered if it could be little green men signaling to us. And if it was little green men, they probably lived on a planet that went round their sun. And there would be what we call a Doppler effect. You've probably all come across Doppler effect, particularly if you've had any small children or have contact with small children. Imagine a small child playing on the floor with a toy car, and the child goes, meow, as he swings the car past him. That change in pitch is what we call Doppler shift. When it's coming towards you, you get a higher note. When it's coming away from you, you get a lower note. If these are little green men on a planet orbiting their sun, some of the time their planet will be coming towards us, some of the time their planet will be going away from us. If we check the frequency or the spacing of these pulses, we may be able to see a Doppler effect. Well, we did see a Doppler effect, but that was due to the motion of the Earth round the sun. So we proved that the Earth went round the sun, but otherwise weren't making a lot of progress. And then I found a second, a third, and a fourth. And it's not little green men. There aren't 4 lots of little green men all choosing the same slightly idiosyncratic way to signal to planet Earth. This has to be some new kind of stellar object. You've probably heard of Fred Hoyle, alas no longer with us, but quite a big figure while he was with us. He was in Cambridge at that time, and having established that we now had 4 of these objects and they weren't little green men and they were somewhere out in our galaxy, it's time to make an announcement. And Tony, my supervisor, gives a colloquium, a talk, and it's given a very titillating title, and every astronomer in Cambridge comes. And Fred Hoyle sits in the front row. 2 possible things could they give these strings of regular pulses. There could be something that's oscillating, sending shock waves repeatedly up into an atmosphere. This is what Tony favors as a model. Or it could be something rotating, a bit like a lighthouse, with a beam that sweeps across us once every rotation. But Tony favors the oscillation. Every astronomer in Cambridge comes to the talk. Fred sits in the front row. Tony gives his talk and says he thinks it's probably one of these oscillating white dwarfs. Fred Hoyle is the first to speak when Tony finishes, and it's open for questions and comment. He had a broad Yorkshire accent, which I'll attempt to mimic, having been at school in Yorkshire. This is the first I've heard of these things. I don't think it's a white dwarf. I think it's a supernova remnant. And such was Fred Hoyle's brain, such was the caliber of that scientist, that within 40 minutes of hearing about these things, he's hit the right explanation. It was probably 6 or 9 months before we were able to verify that he was right, but it came. The name Pulsar, which is now commonplace, was coined by the science correspondent of the Daily Telegraph, Anthony Michaelis. Daily Telegraph is a rather right-wing newspaper, not one that some of us read very much, but read by a lot of the country and definitely reputable. And he said, what are we going to call these things? And we thought about that, because to publish, we had to decide whether it was a pulsed radio source or a pulsating radio source. And we went for pulsating radio source because pulsed might imply some living being making it pulsed, little green men. So we had the answer for Anthony Michaelis. Yes, they're going to be pulsating radio sources. No, he says, you want a short name. What about Pulsar? A bit like Quasar. And Pulsars they became, thanks to Anthony Michaelis, a very good science correspondent of that newspaper. So what are they? We now know they are very compact stars with large magnetic fields that spin pretty fast. The video on the left shows a rotating star. It's got an offset magnetic field, and coming out of the magnetic poles are those yellow cones. Those are beams of radio waves. And if the radio wave shines in our face, we see a pulse once every rotation. If it doesn't shine in our face, we don't see it. So we only see a fraction of pulsars. And this is the static version. Here is this very small 10-kilometer radius star, same mass as the sun, magnetic axis, rotation axis, spin axis, and the beam somehow is formed and comes out constrained by the magnetic field. We probably only see about 1 in 5 of all pulsars, or could see about 1 in 5 of all pulsars, we estimate. We'd have to go elsewhere in the galaxy to see see some others. So they're very small, they're very dense, they're rich in neutrons, a radius of about 10 kilometers, very strong electromagnetic fields, probably formed when a massive star explodes at the end of its life. It's the core of the massive star, and in the explosion, it gets kicked against and gets compressed. And we primarily observe them as radio emitting objects, but they are also seen, some of them, in X-rays and gamma rays. Very, very few seen in the optical. Several thousand known now, surprisingly large number in gamma rays. About 10% of them in binaries. We know of one with its triple system. We know of a few that have planets. Now, I can give you several very good reasons why there should no longer be planets around a pulsar, but in some cases there still are. So, as I said earlier on, Tony favored the picture of an oscillating object launching shocks regularly into its atmosphere, and others preferred a rotating object. You can tell the difference if you can watch, monitor, measure the pulse period phenomena, because with an oscillating object, as it gets tired, it quivers faster and faster and faster, and then stops. Whereas with a rotating object, as it tires, it gets slower and slower and slower. When the pulsar in the Crab Nebula was found, the Crab Nebula is the remains of an exploded star. There's a pulsar about there. It's a very good pulsar for doing measurements on. It's one of the strongest and fairly fast. And when this pulsar was discovered, they managed to measure how the period was changing with time. And the period is increasing. Period is getting longer. In other words, it's getting slower. So they are rotating objects. They're formed, we believe, when a massive star explodes in what's called a supernova. So this is part of a large Magellanic Cloud. It's 1987. Very early 1987, the sky looked like this without the arrow. The arrow's added afterwards. But in February 1987, that very inconspicuous star exploded and presumably created a pulsar, a neutron star, which we have had great difficulty observing. We now have evidence that there is something in the center of this remnant. We have not yet seen it pulsing, but at least there is something that's heating its environments and probably is a pulsar. I think I've said all of that. I've probably said a lot of this as well. So they're created when a massive star explodes. We see them primarily in the radio, also X-ray and gamma ray. They're very rapidly spinning. They have a very small radius, of phenomenal mass, huge density, huge electric field, huge magnetic field, and a very exotic, extreme interior structure. So for those of you who are physicists, this is the problem you have to solve. High acceleration due to gravity, high gradient of acceleration due to gravity, high angular velocity, high density, high electric field, high magnetic field, all at the same time. And I'll take, just to finish, a few minutes more, if that's okay, to tell you a few stories about how pulsars were nearly discovered. Because one of the privileges of having discovered pulsars is every so often somebody would sidle up to me at a conference and say, you know, I nearly discovered pulsars, and tell me the story. And the stories are quite illuminating. So it's 1957. We are in Texas at McDonald Observatory. There's an 82-inch telescope, and part of McDonald's endowment was that it was open to the public one night a month. It's that night of the month, and a student who's just graduated from Chicago is there as a summer intern. And members of the public step up to the telescope. It's looking at the Crab Nebula and that funny star. And they say, ooh, and wow, and gee, or whatever people said in 1957. And one young woman steps up and says, that star's flashing. And the night assistant starts to explain about scintillation, twinkling. And she stops him and she says, no. My job is to fly newly constructed aircraft from the manufacturer to the customer. This is 1957, and this young woman holds a pilot's license, and that's her job. She goes on, I fly at night. There's not much to do in the cockpit at night. So I look at the stars, and I know about scintillation. That star's flashing. Now, the Crab Nebula star flashes 30 times a second. It's fairly fast, but some people can see that frequency. It used to be the frequency of the main supply in Canada. And the people who are best able to see that frequency are young and female. So we do think she saw it, but nobody would believe her and nobody followed up. Roll on to 2007, and the Australian radio astronomers who do pulsar work suddenly get an email from an excited American, Charles Schistler. He worked for the military as a technician in the Alaska early warning radar system. And when things were quiet, he was allowed to play around with the radar. And sometimes he used the radar receiving equipment just to look at the sky. And he found pulsing things, which were not incoming ballistic missiles. He'd done an astronomy course at college. He knew about right ascension declination. He made a note of the right ascension and declination. And illegally, because he shouldn't have done this as a USAF person, he kept a note of the right ascension and declination on a slip of paper, which he took with him when he left that service. He's just discovered the online Pulsar catalogue, and several of the right ascensions and declinations match, including the Crab Nebula. The Australian radio astronomers worked with him and think he was genuine. Sue Simpkin was at this time working in ultraviolet spectroscopy. She's got some time on the telescope. A Dutchman, Lou Vulture, asked her to take an ultraviolet spectrum of that funny star in the middle of the Crab Nebula. Sue takes the spectrum. She says the spectrum's pretty dull, but as she's taking it, she notices what she calls waves going out. Now, Sue started life in Canada at the time when Canada's main frequency was 30 hertz, 30 times a second. Sue is one of that category of women who can see 30 hertz. When she told Lou Vulture about these funny rapid waves coming out, he didn't believe her. But when pulsars were discovered, in particular when the Crab pulsar was discovered, he said, you probably saw it. And there was a survey of the radio sky being made at 408 megahertz using the largest available telescopes. It's nearly complete. There's one or two pesky little bits of sky they still have to observe. And early one morning, about 3 o'clock in the morning, one of the pen recorders, which was known to be temperamental, starts going weep, 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 weep. And the astronomer in charge says, oh, damn that pen recorder, and does what we always did, you thump it. So he thumped it and it stopped going weep, weep, weep. And he said, oh, good, put on his coat, went home to bed and didn't make an entry in the logbook. That weep, weep, weep was not the pen recorder misbehaving. He had observed a pulsar that we now know is in that part of the sky, quite a strong pulsar. But because there was no entry in the logbook, he couldn't claim prior discovery. I'm going to skip factors that led to the discovery. I've blathered on far too long and say thank you for your attention and thank you for your interest.
Jocelyn, I don't think you've gone on far too long at all. Thank you very much for a fantastic storytelling description of a very complex phenomenon that you have personally been involved with. I do hope that you hold on to those tools and that you don't use them in your garden, because they are very, very, very special. Yeah, and for listening to you again, it just highlights the need for scientists to look out for those patterns and to be very, very persistent and diligent in their work. And I think they're fantastic skills that you obviously have had and have done you a great service. Just a reminder to people, we do have a couple of minutes before we finish. So if you do have any questions for Jocelyn, I'll try and keep an eye on them. There's lots of praise and thanks coming in your direction, Jocelyn. There was a question from Kate earlier on regarding the telescope that you worked with. I think the 4.5 acre, is that still operational, or do you know if there's anything on the site?
The telescope has fallen down, basically. It was fairly simple construction. Wires have rusted away, wooden posts have rotted, and there's basically nothing left of it anymore. Sadly, but tempus fugit.
Yeah, I suppose they in your time, it took a long time, and they still are a complex construction, even if they are made of relatively simple material. And something comes along, I'm prompted to mention that we now here in Ireland have ILOFAR, which is part of the frequency array, and there's some fantastic work being done with that, but it's not the type of telescope that one visualizes in the form of an optical or a dish. Okay, I'm just going to pick up a couple of those questions as I see them come in. So Cormac has asked, could you say a little bit about those factors that led to the discovery?
Thank you. I think one of the important ones was I was a graduate student, so I didn't have a lot of other responsibilities that could have distracted me. And I actually think a major one was this imposter syndrome, that I was all the way through convinced they were going to throw me out. And so I was working really hard. Many people suffer imposter syndrome, you know, when you start a new job, let alone when you start a new course at college. And I would commend to anyone who's feeling it that it's quite a good technique just to work as hard as you can. So I think that was probably a major factor. I was trying to make sure I wouldn't have a guilty conscience when I got thrown out.
Very good. There's loads of comments coming in that this story that you've told needs to be presented to our students to encourage them, particularly females, into the world of physics. And that is, I know, one of the aims of this year's summer school. Yeah, the comments coming now fast and furious, and the questions. Are any pulses lined up with the axis perpendicular to our line of sight, so that they give two pulses per rotation?
Yes, there's one or maybe two that do. It obviously needs pretty precise alignment because the beam is actually quite narrow. But yes, there is, it says, at least one, and probably a few that do. But they're rare because we now have 3,000 or 4,000 pulsars. So you don't count on finding them.
Okay, thank you for that. Let me see. Okay, I'm just trying to pick out those questions from many chats there. Okay, are there any assumptions made? Made about example using half lambda for the interferometry? Also, was it a coincidence that the QSO was of the same order of magnitude as the array?
So the first part of that question, the half lambda, refers to the size of the actual antennae, the individual elements that make up the radio telescope. They were half wave dipoles. Full wave dipoles would have had a size of 3.7 meters. And that's really rather large. It's good sense working with half lambda, and it works almost as well as full lambda and is a good deal more manageable. I don't understand the second part of that question. I'm afraid that the quasar was the same order of magnitude as the array. I'm sorry, I don't.
Okay, maybe that person can post in their question there again, and maybe Jocelyn, we can read it out again. Michael Keating says, thank you. I've just finished reading your paper. A Quaker astronomer reflects, and he read it with his 13-year-old child. And the comment is, you make astronomy very accessible. Thank you very much for your wonderful talk. I could listen to you, for hours. Okay.
Thank you.
Yeah, so sometimes on the chat, the words are split across my screen, and that's the problem. There is a comment, no pressure now. What are your views on what dark energy and dark matter are?
Right. Well, the first thing to say is I do believe they both exist. Some people would like to, wish them away as being an experimental artifact or something like that. But I think we do live in a universe where there is a lot of, quotes, matter that we haven't yet sussed out, found. We can see evidence of it. We don't know what it is. So being both romantic and a bit stupid, we simply call it dark matter. And then the other issue is, you probably know that the universe is expanding, that it began with an explosion that we call the Big Bang, and it's been expanding, coasting out ever since then. You'd expect the coasting out to gradually slow, but it appears that instead of slowing, the coasting out is getting faster. So something's pushing it apart. And we call this dark energy. The word dark in both these cases means we haven't a clue what it is. And we still haven't much clue what it is. At least I certainly haven't. So yeah, the universe is not as we thought it was, not that far back. We're learning more about it and discovering that there's a lot more going on than we had originally thought.
Okay, and of course, the work that you did and the astronomy group that you mentioned, there was the presentation of the Nobel Prize. It has been well documented that you weren't credited to that. Could you speak just briefly regarding that for us?
Yeah, this goes back a very long way to mid-1970s, I would guess. The Nobel Prize was awarded to Tony Hewish, who is my supervisor, for the discovery of pulsars, and at the same time to Maarten, who was the head of the radio astronomy group, for the technique he developed for making maps of radio sources, a technique called aperture synthesis. And I was actually very pleased at that announcement. There is no Nobel Prize in astronomy. And this was the first time that the Physics Prize Committee had recognized that there could be good physics in astronomy. So it was a major milestone from that point of view. And I could see that it opened a door, created a precedent, and that in years to come, other astronomers would get the Nobel Physics Prize. And that indeed has turned out to be true, as I'm sure a lot of you will know. Probably about 15, at a guess, astronomers have had the Nobel Physics Prize since then. So my intuition was absolutely right. I've also discovered that you can do very well out of not getting a Nobel Prize. If you get a Nobel Prize, you don't really get anything else because people feel they can't match it. If you don't get a Nobel Prize, you get every other prize that moves by way of compensation. So I've had a lot of fun getting other prizes and traveling to interesting places to receive them. It's been good fun.
That's excellent, Jocelyn. Thank you. We'll maybe finish on this final question, maybe that Rose asks, and it goes back to your toolkit. And which of the items was most frequently used, if you can remember?
Whoa, they've certainly all been used. I must say they are the only pliers I have. They are the only wire cutters I have. I do have some other screwdrivers of various sizes and with different heads. So I'd say the screwdriver is the least used, but I wouldn't want to choose between the others to say which was the most used.
Very good. Excellent. Excellent. Okay, we're just gone over the 3 o'clock, so we will adjourn for now.